Jai Jagannath. So, welcome to More Physics. So, uh, today we will start lecture number 4 of electric potential. So far we have already discussed the potential due to electric dipole, potential due to point charge, and we have solved some numericals. So, today we will start with equipotential surface. So, what do you mean by equipotential surface? From the name it indicates, it is a surface on which at each point potential is same. Okay, so this is the definition. It is that surface where potential at each point on the surface is equal. Suppose I will take a point charge, isolated point charge. Isolated means only one charge is present. So if I will draw a sphere, if I will draw a sphere of radius r, then on the sphere, if I will take 2 points or 3 points, suppose this is 1, 2, 3. So what is potential at 1? So you know V1 is equal to KQ by R. What is V2? V2 is also KQ by R. What is V3? It is also KQ by R. So that means potential at every point on this sphere is same. That's why this surface, this spherical surface for this isolated charge is called equipotential surface. So this is your equipotential surface. Okay. So now, if you will take a linear charge conductor, suppose I will take, this is a linear charge conductor. The charge is uniformly distributed. So for this type of linear charge conductor, what is the nature of equipotential surface? What is the nature of equipotential surface? So now you take a cylinder. Suppose this is a cylinder. Okay, and the cylinder, the axis of the cylinder is coinciding with the linear charge conductor. So here every point on the surface of the cylinder is at equal distance from this linear charge conductor. So potential at every point on this surface of the cylinder is equal. So that indicates the cylindrical surfaces are equipotential surface for which type of charge conductor? Linear charge conductor. So if I take another concentric cylinder, the concentric means their axes are same. So this is also this second cylindrical surface is also equipotential surface. Okay. So now you see here at this point, suppose I will take, this is the A surface, this is B surface. Here potential at A and here potential at B. Out of VA and VB, which is greater? Definitely it is nearer to the positive charge. So here potential is more than potential at B. So potential at A is greater than potential at B. And what is the direction of the electric field? Direction of the electric field is away from the positive charge conductor. So this is the direction of the electric field. So what we observe here, the potential, here it is more, here it is less. That means potential falls along the direction of electric field. So we can write along the direction of electric field, potential drops. So that this concept also I had given in the last video. Okay, so this is about the equipotential surface. Next we will start properties of equipotential surface. Properties of equipotential surface. You see, first property, no work is done by carrying any charge between any 2 points on equipotential surface. Suppose let us just take the example. Suppose this is a sphere. At the center there is an isolated charge Q, and we know for the isolated charge the equipotential surface is spherical in nature. So now I am taking 2 points A and B. I am taking A and B 2 points. So I want to carry a charge from A point to B point. So we have to find what is the work done. So what is the formula of work done? Work done from A to B is nothing but the charge into potential difference VA minus VB or VB minus VA, whichever. If the work done by the if the work is done by the electric field, it is VA minus VB. If the work is done by the external force, then it is VB minus VA. So, but what is the magnitude of this charge? This is the value, and that is equal to Q naught into. Since it is equipotential surface, potential at A is equal to potential at B. That means the potential difference is equal to 0. That means work done is equal to 0. So no work is done by carrying any charge between any 2 points on an equipotential surface. Clear? Second point. The direction of electric field is always normal to equipotential surface. Now see, suppose this is the equipotential surface, spherical sphere, spherical surface. This is the charge at the center. Now I am taking 2 points, that is A and B. They are very close to each other. Okay. So now what is the direction of the electric field? This is the direction of the electric field. Electric field is always radially outward direction if the charge is positive. So now you know what is the work done formula. So work done, you know, that is the E dot dl integration from A to B is equal to work done. Okay, so that is for unit charge. So if you will take Q naught charge, then work done is equal to this. So now you see, if A and B are very close to each other, then distance between A and B is very small. If it is very small, there is no need to take the integration. In that case, integration we can remove. So this is E dot dl is equal to WAB by Q naught. So here you see, since A and B both are lying on the equipotential surface, the potential difference is equal to 0, and since potential difference is 0, the work done is also 0. We have already proved in the first property. So here work done is equal to what? 0. That means E dot dl is equal to 0. And this is the condition of perpendicularity. You know, if A vector dot B vector is equal to 0, then A vector is perpendicular to B vector. So similarly, E dot dl is equal to 0 indicates E dot dl is equal to 0 indicates E is perpendicular to dl vector. That means that implied electric field is perpendicular to the equipotential surface, because dl lies on the surface and electric field must be perpendicular to the surface. So this is the second property. Come to third property. When all charges are at rest, the surface of a conductor is always an equipotential surface. Now you see, suppose you will bring a electrical wire from the market. In that electrical wire, the charge are at rest. They are not moving. Okay. So if charge are at rest, then the work done will be 0. You know, what is the definition of work done? Work done is equal to F dot S. That is Fs cos theta. So if displacement is 0, work done is 0. That means in a electric conductor, when charge are at rest, when charge are not moving, at that time work done will be 0. And we know if the work done is equal to 0, then the surface is equipotential surface. So all the conductor, when all the charges are at rest, the surface of a conductor is always an equipotential surface. So next property, two equipotential surfaces can never cross each other. Okay, suppose you see, this is an equipotential surface. This is another equipotential surface. So these two equipotential surfaces can never cross each other. We will prove this in negative way. That is, let us say that two equipotential surfaces, this is A and this is B. So these two equipotential surfaces are intersecting or crossing at which point? At O point, at this point. So now you know for equipotential surface, electric field is perpendicular. So now if I will assume this is my equipotential surface A, at this point, what is the direction of electric field? Electric field is perpendicular. So this is the electric field at this point due to A equipotential surface. And if I will tell that this B is my equipotential surface, and at this point, what is the direction of the electric field? It is perpendicular to the B surface. Now you see at the same point we are getting two different direction of electric field, which is never possible. So if at the same point two different direction of electric field is not possible, then intersection of two equipotential surface is also not possible. Last property, for uniform electric field. You see, uniform electric field means suppose this is the lines of force. Okay, so these are the electric field. Uniform electric field means the strength of electric field is the same everywhere and direction of electric field is also same. And these lines of force are equispaced. So it indicates this is uniform electric field. So you know for uniform electric field, the charge must lie at which point? Infinite distance. Just like sun. Sun is situated at infinite distance. So all the rays are coming to be parallel with each other. So in that way, if charge is at infinity, the electric field are uniform and they are parallel to each other. In this case, what is the nature of equipotential surface? Now see, suppose this is a paper, this is a plane. So this plane is perpendicular to the electric field. And we know for equipotential surface, the electric field is always perpendicular. So here for this type of uniform electric field, so this is a plane which is perpendicular to the electric field. And if this is another plane, this is also equipotential surface which is perpendicular to the lines of force. If I will take another plate, so this is also equipotential surface. Clear? So now you see, let us say this is my A surface, this is your B surface, this is your C surface. So this is A, B, C, three planes. They are parallel to each other because every surface is perpendicular to the electric field. And we know for equipotential surface, the plane of the equipotential surface is perpendicular to the electric field. So now this is the fifth property, that is equipotential surface are parallel to each other if the electric field is uniform and they are perpendicular. You see, the surface is perpendicular to the electric field. Okay. Another point is that you know what is the value of, what is the expression of E? E is equal to minus dV by dr. I have already explained this. And if you take the magnitude of the electric field, it is nothing but dV by dr. Now for uniform electric field, E is constant. For uniform electric field, E is constant. Okay. So if E is constant, then dV by dr must be constant. So now what I can explain here, suppose at A point the potential is 10 volt. At this surface and at this point also 10 volt, at this point also 10 volt because it is equipotential surface. Come to second plate. In the second plate, the potential at this point is not 10 volt. Either it is less than or more than. So can you suggest me? Okay, you can't suggest me because I can't see you or hear you. Anyway, so here at this point, potential is definitely less than 10 volt because the electric field direction, we know the potential drops along the direction of electric field. Just again I am explaining like this. Suppose this is the positive plate, this is negative plate. This is the direction of the electric field. Okay. So here positive negative means here higher potential, let us say 10 volt. Here lower potential, let us say 0 volt. So here you see, so electric field always from positive to negative plate, that is higher plate to lower plate. That means potential drops along the direction of electric field. Okay, so here electric field is towards right, here potential is 10 volt, definitely here potential will be reduced, let us say it is 8 volt. So here potential again decreases, let us say it is 6 volt. Now what is the distance between A and B plate? Let us say R1, and distance between B to C plate is also R2. Now what is the potential difference between A and B? 10 minus 8, that is 2 volt. So what is the potential difference in between two plates? 8 minus 6, that is also 2 volt. So here electric field intensity is constant. Potential difference between two plates is constant, that is dV is constant. So if E is constant, dV is constant, automatically dr is constant. Dr means distance of separation between two plates. So that implied here I can say R1 is equal to R2. That means if the potential difference are same, then the distance between the two plates will also remain same, provided electric field intensity is constant. Suppose I will take a spherical, suppose this is a point charge. Now near to the charge I am drawing a radius of R1. This is a sphere of radius R1. Another sphere of radius R2 I am drawing. This is your, suppose B sphere, this is A sphere. Another radius, let us say this is R3. So I am drawing another sphere of R3. And you can say the A sphere is equipotential surface, B sphere is equipotential surface, C sphere is also equipotential surface. Let us say so what is the direction of the electric field? If this is positive charge, electric field is always away from it. And we know along the direction of electric field, potential drops. So let us say at A, potential is 10 volt. At B, potential is definitely less, that is 8 volt. Let us say at potential at C is equal to 6 volt. So what is the difference you see? From A point to B point, what is the potential difference? 2 volt. From B point to C point, what is the potential difference? Again 2 volt. So here potential difference between two spherical cell is equal to 2 volt. Then why? So what is the, let us say the distance of separation between A and B is R1. Let us say D1. And distance between B and C is say D2. So distance between A and B is D1. Distance between B to C is D2. Now here you see, from A to B, potential difference is 10 minus 8, that is 2 volt. And from B to C, potential difference is 8 minus 6, that is 2 volt. So here 2 volt, here 2 volt. But here distance of separation is less, here distance of separation is more. So can you justify this? You see, what is the formula? E is equal to dV by dr mod. So now you see, here E is not constant, here E is variable. So nearer to the charge, E is more. So nearer to charge, E is more. If E is more, dV is constant, because we are maintaining same potential difference, 2 volt. So dV is constant. So if dV is constant, E is more, definitely distance of separation is less, because E is inversely proportional to dr for constant potential difference. Okay, so you can say E is inversely proportional to dr for constant potential difference. So here nearer to the charge, electric field intensity is strong and dr is less. And if we will move away from the charge, electric field intensity will decrease, distance of separation will increase. So this is the logic behind it. Now potential gradient. Now see, I have already told, let us say A point and B point, the potential difference between A and B is equal to VA minus VB is equal to line integral of electric field from A point to B point. Okay. So now if A and B, if A and B are very close, then the VA minus VB, which is equal to potential difference, is also, let us say, very small. So if potential difference is very small and A and B are very close to each other, so there is no need to write the integration. So here dV is equal to what? E dot dl. So this is the work done by the electrostatic field. But if I will tell the what is the actually potential difference? Potential difference is equal to actually final minus initial. Okay. So here I can write the potential. So this is your VA minus VB. But actually potential difference, we take final potential minus initial potential. So if we take final minus initial, that is VB minus VA, so it is equal to what? Minus E dot dl. So this VB minus VA is nothing but dV. So dV is equal to minus E dot dl. dV is equal to minus E dot dl. Okay. So now you see, if there is an electric field in the space, we can write the electric field in component form, that is Cartesian form. So electric field intensity has X component, it is Ex I cap, Y component Ey j cap, Z component Ez k cap. Similarly, suppose you see, this is Y axis, this is X axis, Z axis. So I am taking a small element dl. Now this dl has which component? X component, that is dx. Y component, dy. Similarly, if it is in the space, it has a dz component. So dl vector can be represented by its S component dxi, dyj, dzk. So this is your dl vector. This is your electric field vector. So now we want to find the potential difference between 2 points which is separated by very small distance, that is dl. So dV is equal to, what is the formula? dV is equal to minus E dot dl. In place of E, you write Exi, Eyj, Ezk. Dot dl vector is equal to dxi, dyj, dzk. So now take the dot product. So if you take the dot product, then what will, so minus Exi dot dxi, that is minus Ex dx plus, this is also minus. So minus Ey dy minus Ez dz is equal to dV. Clear? Now I want to find what is the value of Ex. So Ex is equal to what? dV. Ex is equal to minus dV by dx. So if I can write Ex is equal to minus dV by dx, provided this term is equal to 0. That means dy is equal to 0, dz is also 0. That is only possible when y and z are constant. You see, if y is constant, dy is 0. If z is constant, change in z is 0. So this will be 0, this will be 0. Then what is Ex? Ex is equal to minus dV by dx. So Ex is equal to this, but we can write in other way, Ex is equal to minus. So when y and z are constant, you are differentiating v with respect to x. So that term is called dou v by dou x. That is Ex is equal to minus dou v by dou x. This is called partial derivative of v with respect to x. Similarly, I can write Ey is equal to what? Minus dv by dy when x and z are constant. So that is called minus dou v by dou y. Similarly, Ez can be written as minus dou v by dou z. Clear? So finally I can write E is equal to, what is the expression of E? Ex I cap, Ey j cap, Ez k cap. So in place of Ex, write down minus dou V by dou X. Okay. So Ex I cap. So I am multiplying here I cap. Similarly, Ey j cap. So Ey is equal to this into j cap. So I am bringing j cap towards left, that is minus dou V by dou Y, plus Ez k cap. What is Ez? Minus dou V by dou Z. So k cap minus k cap dou V by dou Z. So that things can be written as minus, okay. So minus, keep it minus. So that is I cap dou by dou X plus j cap dou by dou Y plus k cap dou by dou Z, and I am taking V common. Okay, so now you see, so this expression and this expression is correct. So that is equal to this is your minus, and this term, this total term is called a function. So that is represented by inverted delta. So that is minus this into V. So this symbol, what is this symbol? This symbol is nothing but what? I dou by dou X, j cap dou by dou Y, k cap dou by dou Z. So this is called grad. This function is called grad. Okay. Or you can say the electric field intensity is negative. Potential, V is potential. This is gradient. So electric field intensity is negative potential gradient. So you can say electric field is negative potential gradient. Negative potential gradient. That is dV by dl. Okay. So this is called negative potential gradient. So why negative? Negative sign indicates what? This negative sign indicates what? Electric field, along the direction of electric field, potential drops. Potential drops along the direction of electric field. So here electric field is in negative of potential gradient. That means, so along the direction of potential drop, or you can say along the direction of electric field, potential drops. That's why this negative sign comes into picture. So you can write negative sign indicates potential drops along the direction of electric field. Okay. So if the electric field is in radial direction, I can say E is equal to minus dV by dr. If it is in radial line, I can say E is equal to minus dV by dr. So this d by dr is called grad. Okay. So on this we can solve the problem. Now see, suppose this is a uniformly charged ring. Let us say this is positively charged ring. Okay. So what is the value of charge? Q. This is the center. This is the axis. Suppose I will take a point P, which is at x distance from the center, and radius of the ring is A. So we have already found that potential at P point is equal to what? We have already derived in the video in the last video. So Q by 4 pi epsilon naught square root of A square plus x square. So if you have not seen this video, so please refer to that video. So this is the potential. I want to find electric field intensity at P. So this electric field intensity at P also I have derived during electric field chapter. So which was calculated by taking integration method. So the total y component will be cancelled, s component will remain. So in that case we can find, so it will take more time. But if the potential at P you know, how can you find the electric field intensity? So what is the formula of electric field intensity? Electric field intensity is equal to minus dou V by dou R. If it is in along x direction, I can write it as minus dou v by dou x. Or you can say, since here potential, so the potential is function of x only, so we can write minus dv by dx, no problem, because there is no other constant y and z. So that implied ex is equal to minus derivative of potential. What is the potential? Q by 4 pi epsilon naught s square plus x square integration. So if you integrate this, you know the integration. So you know the integration, you just you know the derivative differentiation. You just differentiate this, you will get what? Qx by 4 pi epsilon naught x square plus a square 3 by 2. So you can integrate this. So this is the formula. And electric field intensity is away from the axial point, away from the center, if the charge is positive. Now, this is test your understanding 23.5. You see, in a certain region of space, the potential is given by this. Potential is a function of which coordinate? X and y coordinate. A, B, C, D, all are constant. So which statement about electric field is correct? There are 4 options. Okay. So now you see, first we will find what is the electric field intensity. How will you find the electric field intensity? You know electric field intensity, if it is a vector quantity, it has x component, y component, z component. So this is the electric field. So what is Ex? Ex is equal to minus dou v by dou x. Okay. So here minus dou by dou x. So what is V? V is equal to A plus Bx plus Cyq plus dxy. Now differentiate with respect to x. And when you are differentiating with respect to x, you are taking partial derivative. At that time, other variables are assumed to be constant. That is here y is constant, only variable is x. Okay. So now a, b, c, d all are constant. So what is the derivative of a? 0. So minus leave it. So 0 plus derivative of bx is b. So here cy d, so cyq is constant, derivative is 0 plus. So what is the derivative of dxy? D is constant, y is constant. So dy. So this is your ex. So ex is equal to minus b plus dy. Similarly, we can find ey. Ey is equal to minus dou v by dou y. So that is equal to, you see, you have to differentiate this v with respect to y. When you are differentiating with respect to y, x is assumed to be constant. So here derivative of a 0, bx is 0. So derivative of cyq is equal to 3cy square plus. So derivative of y. So here dx is a constant. So this is the value of ey. So now I can write. So I can write what is the value of E. So so now you see what is Ez. Ez is equal to minus dou v by dou z. So here there is no z, all are constant, that is 0. So I can write E is equal to Ex. What is Ex? Minus b plus dy I cap plus Ey j cap. What is Ey? This is minus 3cy square plus dx j cap. Okay. So now you see first option, if A increases, E increases. You see, electric field intensity is independent of A. There is no term of A in this expression. So option A is not correct. Similarly, in option B, if A increases, E decreases, it is valueless because electric field intensity is independent of A. And third option, electric field intensity has no Z component, definitely. So electric field has which, so there is no Z component, there is no K cap. So the third option is correct. Electric field has no Z component. Fourth option, electric field intensity is 0 at 0, 0, 0. So now, what is electric field intensity at origin? S0, Y0, D0. So put x, y, 0 here. So if you put y 0 here, it is minus b I cap. If you put x 0, y 0, here you will get j cap. So electric field intensity at origin is equal to minus b I cap. It is not equal to 0. So this option is also not correct. So this is the C option.